So I shouldn't be talking for too long today. All I want to do is just go over the basic gates again. If you're worried about finite state machine stuff, I'll be going over that on Thursday, and the lab on Thursday is going to deal with finite state machines. I didn't want to bog you down and make you have to do anything finite machine related immediately after you learned it, so that's on Thursday. For today, you're just essentially going to be making an adder, but another thing that was very quickly covered in the lecture, but that is important to understand, is the concept of basic memory gates. So we only cover a couple of them. There's quite a lot of different memory circuits, or basic memory circuits, but the first one I'm going to talk about is just the SR latch. And SR, the reason that there's the SNR here is because it's set and reset. And that it basically is pretty much the simplest possible gate that you can make. So the sort of problem here is, like, if I make a table for an SR latch, and this right here is Q next. So the whole point when you're dealing with memory is that you've somehow introduced an ability for a circuit to remember something, which is a little bizarre at the beginning, but you get used to it. And so it has a current output, Q current, but it also has a next output. And you'll see how that fits in. So then we can look at all the possible inputs for S and R. So when both of S and R are 0, Q next is just going to be Q current. So what that means is it's just going to stay whatever state it currently is. If R is 1 and S is 0, then it's going to change the state to 0. It's going to reset it back to 0. If S is 1 and R is 0, it's going to set the SR latch to a 1. And this is an invalid input. Just, it's not supposed to be used. Essentially, if you look at how SR latches are made, if you try to input a 1-1 into S and R, it just ends up breaking everything. So that's not a valid input. We only need to worry about these first three. So if you were to, let's say, just convert this into an equation like you did for the multiplexer, you could maybe say, okay, it would be not S and dot R times QC, and then S not R. This is an SR latch, period. It's not, an SR latch is not necessarily created out of any gates. An SR latch is a memory component that is defined with this behavior. Anything with this behavior is an SR latch. I'll get into how you can make SR latches, but that's technically a different topic. By definition, anything which satisfies this behavior is an SR latch, where, also 1-1 is undefined. The same way, like an AND gate is just a table, right? You can draw the atomic component AND gate, or you could make an AND gate out of NOT gates and OR gates if you wanted to, right? And this is just an application of De Morgan's law, right? These are both AND gates. It's just one is made with NOTs and not in OR gates. Yes, there is a slight difference between how they're exactly made, but their behavior is the same. But yeah, so if you just tried to come up with a sum of products form, you would get that Q next equals not S, not R, QC plus S not R. And QC isn't an input, it's the current output. So you have you would have to have a circuit here. You'd have to have your S, your R, Q current as an input, and then Q next, and then you'd somehow connect this up back up to here, and it just starts to get really confusing about how you're supposed to implement this. So I'll sort of I'll try to instill the intuition behind how a basic SR latch works. And although, as I just said, this table, anything that sort of works like this table is an SR latch, which is also why you can make one with NOR gates or NAND gates, right? As long as it works, it's an SR latch. Really, what you might start with, if you're trying to create some sort of memory within a circuit, you might start off with this thing here, which seems a little bit weird, but let's just, assume there's some external power coming to this. Typically with circuits, that's how it works. But if you think about it, if this wire here is a 0, well, it'll be inverted to a 1 over here. Well, this one's going to be passed into this NOT gate, and then it'll be a 0 over here, right? And so this is stable. It's never going to change. It's always going to be 0 on this side and 1 on this side. However, what if I take the same exact thing, and instead I say, well, what happens if this side's a 1? Well, if this is a 1, this will invert to a 0, and this 0 will invert back to a 1. And this is essentially the basis for how an SR latch works. Now, ideally, we would want to be able to toggle between these two states, right? We have this loop here, and we want to be able to change it from one to the other. And like if you would think about it, if I could somehow magically change this 0 to a 1, well, then this 1 would invert, become a 0, and come over here, and then the 0 would invert to become a 1, and it would become stable, right? We can't just like inject a 1 onto a wire or something like that, but we can use a logic gate to do so. So right here, if I instead put an OR gate, I can call, I don't know, let's say we'll call this S. So now, here, if I pass a 1 into here, let's say this side is a 0 and this side is a 1, and this input is just 0 here, right? Well, this is going to be 0. 0 or anything is just going to be, or 0 or 0 is going to be 0. Invert that as a 1, invert that as a 0, right? So this is in a stable state here. If I turn this S into a 1, well, 0, or 1 or 0 is going to be 1. Invert that will become 0, which will feed back over here. We'll invert back into a 1. And then 1 or 1 is just 1. And so this is a fully stable circuit. But now if I change this S back to a 0, well, 0 or 1 is still 1. And so I've changed the state from being 0 on this side and 1 on this side to being 1 on this side and 0 on this side. And instead of saying, which side the 0 and the 1 are on, I'll say that when this side is I'll basically just say the state is whatever this side is. So on the left-hand side, whatever the number is, that's going to be my output Q. And this looks a little bit weird, but we'll be able to clean it up and it'll look a bit nicer. And if you look here at the table, when I set S to 1, and R just stays at 0, I haven't added the R yet, but if you set S to 1, the output Q should now be 1, right? Whatever it was before, it should now be 1. And that's exactly what happens. No matter what state you're currently in, if you change this to a 1, wait a little bit, then Q will eventually be 1. And once you set S back to 0, it'll just stay that way. Nothing's going to change in the circuit, which is exactly the sort of behavior this first row is supposed to do. For reset, you just add an OR gate here. And you get the same thing. Right? So here we can say this is R. And so now, let's say I want to reset this back to 0. So let's say I set R to 1. Well, 0 or 1 is just 1. Invert that as a 0. So now this side becomes a 0. 0 or 0 is 0. So this is a 0 here. Invert that becomes a 1. So this wire is going to become a 1. 1 or 1 is 1. And so we've stabilized. And now we can see that our Q here is 0, which is exactly what's supposed to happen when you set R to 1. But when I set R back to 0, well, 1 or 0 is still 1. So this circuit stays in its stable state. And it just maintains whatever it was, which is exactly what this behavior does. And this is at least one of the many ways that you can make an SR latch. And this is with the NOR gates, and it makes a little bit more sense to me how you might come up with an OR gate one. For NAND gates, nothing's really different. It's just applying De Morgan's law to this circuit here. So recall. So here we have like A or B inverted. So we have A or B with not on top. This is the same thing as not A and not B. That's De Morgan's law. So we can sort of distribute the not, but we have to flip what operation we're doing. Instead of or, we have to do and. And so if I go ahead and do that, you'll see we get the second gate. So we can change. We'll have this S here. It'll get inverted into an AND gate, right? And then we'll have this in this thing right here. So I've taken this thing right here, which is the NOR gate, and transformed it into this, and that is a valid operation according to De Morgan's law. Then we'll have the second one here that'll also get transformed into an AND gate with both inputs inverted. Right, and then we would have R here, and this would also, let's see, well, this, because we've inverted the way that, or actually, let's see here. Yeah, so this is actually still Q here, this line right here. Well, this is not what you're used to seeing. You're used to seeing this with NAND gates. Well, what we can do here is, instead of drawing this NOT gate here, we can push it all the way back and turn this AND gate into a NAND gate. So you can sort of imagine just sliding that NOT gate up until it hits the AND gate, and then it becomes an AND gate. Right? And then this right here, instead of just drawing the NOT gate, we'll just say that this input is not R. And then we'll do the same thing with this NOT gate. We'll just bring it all the way over here and change this AND gate into a NOT gate and rewire this stuff up. But now you'll notice that we sort of slid the NOT gate. We slid the NOT gate past this output here. So this is no longer Q. It's actually not Q, which is right here. So that's something you have to notice. And I'll draw them out like the way that they're normally shown, so that this is a bit more clear. But this actually becomes not Q now. It becomes the opposite of Q. And then we can do the same thing here and just make this not S if we want. And then here, this is the latch that you're essentially used to seeing. Again, it's a little bit of a different form. But let me go ahead and redraw them. So what you're probably used to seeing, at least with the NOR gates, is you'll have two NOR gates side by side. We'll have our two inputs coming here. We'll have our two outputs here. And then they're sort of like crossing like this. So now, like if we just take this S here and put it here, well, we can see that, we can sort of go through the NOR gate, through the second NOR gate, and then that's the output Q. So if we go through the first NOR gate, through the second NOR gate, this is the output Q. And that's something you have to keep in mind is in an SR latch, and this is just not Q here, that just corresponds to this side, and it just so happens that it's exactly the opposite of what this side is. As I was saying, one side is always 0 and the other one's always 1. So on one side you have the output Q, on the other side you have not Q, the opposite. And so this right here is an SR latch with NOR gates, and then with NAND gates you can draw the same sort of thing. However, the two outputs swap because that NOT gate sort of passes through here, and suddenly you can't really just get Q out from this side. You can only get not Q. And these inputs become inverted. Really, you could just put a NOT gate here and then just call this S if you wanted to. It's just normally not written like that. I believe the main reason there is just because, for the most part, if you have a circuit that produces an output and then you need to invert that output, it's usually just easier to make the circuit output the inverted value instead. So like, let's say I had something here that outputs an S, and then I was going to use a NOT gate to do that. Well, instead of just putting a NOT gate here, it might just be easier to change this circuit to output not S, and then I don't have to have a NOT gate here, and that's cheaper. So that's usually why we'll just write not S there, because a lot of times you don't actually have to put a NOT gate to do that inversion. You can just invert it somewhere else, and then you don't have to add anything extra to your circuit. But yeah, these are the two main circuits, the two main ways that you can make an SR latch. One with the NOR gates, and one with the NAND gates. And again, so if you're not sure, like let's say you can really just, if you want to label these and you're not sure how to, let's just say you know how to draw this, but you don't know how to label it. What you can do is you can just say arbitrarily which one of these is S and R, and then just assume that it's in one state. I'll just say that right now this wire here is a 1, and these are both 0, let's say. So this 1's going to propagate over here. So 1 or 0 is 1, invert that is 0. So this output here will be 0, and then this will be 0, 0 or 0 is 0, invert that as 1. So we have a stable state here. Well, you know that in an SR latch, when you set S to 1, it's supposed to change the state to 1, right? So if I change this S to a 1 here, well, 1 or 0 is 1, invert that is 0. This would propagate over here. 0 or 0 is 0, invert that is 1. And then this would feed back over here. 1 or 1 is 1, invert that is 0. So now we're in a stable state. But now this wire here has turned to a 1. Well, by definition of how an SR latch is supposed to work, this has to be Q, because otherwise it's not an SR latch. Otherwise it doesn't satisfy that behavior. So if you're not sure how to label it, just quickly do a simulation. Just quickly run through what the values would be. Let's say if you set S to 1, and then you know exactly where that output Q should be. For the NAND gate, you know, let's say you don't know these, and then the other one's obviously not Q. So here, these would be both 1 by default, and that's something you have to be careful of. So let's just say right now this is outputting a 1. So this would be a 1 here. This would be, so yeah, 1 and 1 is 1. Invert that as 0. 0 would propagate over here. 0 and 1 is just 0. Invert that as 1. So this is a stable state. Again, we'll change the state of S to be a 0, right? So here, normally you would set S to 1, but because it's inverted, you set it to a 0. So 0 and 1 is 0. Invert that is a 1. So this would become a 1 here. This one would propagate. 1 and 1 would be 0. Invert that would be or 1 and 1 is 1. Invert that as a 0. This would propagate, and then you're in a stable state. Well, you just told the SR latch to set itself to a 1, and this is the wire that turned into a 1, so you know that's Q, and you know this is not Q. So any questions on SR latches? Well, not S is just not S, right? I could also just do this here. It's saying that it's the opposite of whatever S is. So S is my input, and it just stands for this right here. S is just your S input. It could be 0 or it could be a 1, and then it just gets inverted before it gets passed into the SR latch made with NAND gates. Did that answer your question? S and R both can't be 1, but not S and not R can both be 1, right? Like if these are both 0 here, then the inputs here are both going to be 1, which is fine, right? The problem is that S and R can't both be 1, not that these wires can't both be 1. Right? Like if I just leave it like this here, if I set not S to 1 and not R to 1, that means S is 0 and R is 0, which is fine. This is why I typically don't think of SR latches with this one, because the inputs being inverted does get mildly confusing. Well, it's so that this behaves like a truth table, right? It's so that that this is the truth table for it. Yes, and really the reason that you have to invert them is, you know, because of this whole De Morgan's law thing. If you do the inversion and then you propagate the NOT gates back to the AND gates to transform them into NAND gates, then you also have to push the NOT gates back to S and R, which, you know, makes those inputs inverted. It just for how does the output become the input to the other? It just does. You just take this wire and you hook it up as the input, and that just works. Technically there has to be some amount of delay between things. If everything happens instantaneously, memory doesn't really work. But in reality, when you're making a circuit, it takes some amount of time for the electricity to propagate down this line, and so there is sufficient delay in order for things to propagate. Well, you can set these to pretty much whatever you want, as long as S and R are both 1. You can set them. Well, so that there is no starting point. With an SR latch, there is no initial starting point. You just have to choose an initial state. It could be 0 or it could be 1. So it's like right now, if I do this and I set both of these wires to, let's say, I'll do it in the NOR gate here. So if I don't assume anything about how the rest of this stuff is working, if I set S to 0 and R to 1, what happens? Well, 0 or nothing. There's nothing here, right? It doesn't make any sense. So really what you want to do is you want to say, okay, I'm going to assume S and R just both start off as 0. So it's in this sort of stable state. And then I'll just arbitrarily choose my SR latch to be in state 1. So I'll just say that this is a 1 here. Then this will propagate. 0 or 1 is 1. Invert that as 0. The 0 will propagate here. 0 or 0 is 0. Invert that as 1. So this could be the starting state, or this could be the starting state. Both of those are valid. It's an arbitrary choice. And, it has to start off in one of them. It can't really start off in neither of them, especially if you look at how this would be powered. But yeah, there is no sort of predefined start state. It's going to be in some state, and then you can do operations on it to modify the state. But yeah, for the most part, it doesn't really matter what state it starts off with, because the whole point is really to just set it to whatever. But something that you might see in this course at some point is a table sort of walking through a set of inputs for an SR latch. So I could you could say that, okay, well, this is time over here. So I'm maybe going to start off with input of 0, 0. That means that the state would be maintained. So at the beginning, so this, I'm drawing this horizontally, and this is very different from a truth table because time matters. And that's the definition of a sequential circuit, right? With combinational circuits, if I have my box and I pass it input 0, 1, 0, and I don't know, it outputs 0, 1, whatever this box does. If I input this and it outputs this, and I know this is a combinational circuit, I know every single time I input this exact sequence of things, it's always going to produce this output. Basically, every single input produces a very specific output, and it's only based off of that input, right? There's no chance that I, later in time, I input this, and then suddenly my box is outputting 1, 1, right? That's not a combinational circuit. But a sequential circuit can do something like that, because it could sort of remember something that happened. And you can immediately see that by just the table of an SR latch, especially with this first row here, right? With these two, the output's always going to be the same. If you pass in 0, 1 or 1, 0, the output is always going to be the same thing. However, when you pass in 0, 0 into an SR latch, it just stays what it is. So if the state here is a 0, so if it's currently holding a 0 and you input 0, 0, well, it'll just output a 0. But if the current state is 1, 0, if the current state is a 1 and you input 0, 0, it just outputs a 1. So that would be analogous, to my box here. I have my S and R input. At one point in time, I pass in 0, 0, and it outputs a 1. But at another point in time, I input a 0, 0, and it outputs a 0, right? That's not a combinational circuit. There's no way to make just a truth table and then convert that immediately into an equation and implement that in order to end up with an SR latch. It's just not possible. And so that's why we're really starting to talk about these memory, because it turns out that all sequential circuits are essentially just some amount of memory that's just keeping track of some sort of state, and then some combinational logic that just allows you to figure out how to transform states, which is exactly why we talk about FSMs, because that's exactly what they describe. You have a bunch of states, and you have an ability to move between states according to some rules, right? And really, those FSM diagrams, if you look at the arrows, those arrows are the rules between how you go from one state to the next. But these this is at least one of the main ways that you can make, at least logically, a memory component that can store a 0 or 1 on a circuit board. But yes, back to this here. So you can imagine a sequence over time. So this would be, we're using the same exact SR latch, but now we're just doing things over time. So if I initially input 0, 0, I don't know what state it was currently at. I'll just put an X here. So, and that just means I don't know, you know, if the SR latch was holding a 0, like if there was another column here and it was holding a 0, well, then this would be a 0. But if it was a 1, then this would be a 1. So I just don't know, right? This is my first input, so I don't know. So let's say now I input 0, 1. Well, that means it would reset the state back to 0. So now my output Q here would just be 0 by definition of that truth table. If you set R to 1, and R is the only thing that's a 1, it just sets the output Q to 0. Well, now if I go back to 0, 0, well, 0, 0 just says basically keep the same output that you just had. So that'll be a 0. If I then, let's say, go to 1, 0, that means, oh, change the output to a 1. So now Q is going to be 1. If I again go back to 0, 0, well, it's just saying, again, maintain the state so that the output will just stay a 1. And you can see here that I have 3 columns where I input 0, 0, and I essentially, well, this one doesn't really count because I'm just saying here that I don't have enough knowledge to answer. But right here, you can see that the output is different based on the input. And that's just because there's a sort of time component that comes into play with these sequential circuits. But yeah, the only sorts of questions that we might ask about like SR latches specifically is a question like this, where you're asked to sort of work through a sequence of inputs. Another thing that you might see is like, given the current states, if I have Q current, it's sort of like filling out the table, but yeah, if I have SR and Q current and then Q next, you might be asked to sort of fill out this table. So like here, if this is not time anymore. It's not time. In this case, it is time, because it's basically saying the current state is essentially the thing in the previous column. But over here, it's just saying I'm going to give you what the current state is, and I want you to tell me what the next state is. So yeah, let's say the input here is to the SR latch is 0, 0, and the current state is a 1. Well, by definition, if the input is 0, 0, the next state is just whatever the current state is. So it would just stay a 1, right? But if I had, let's say, 0, 1, and my current state was a 1, well, this says reset it back to 0. So that means, you know, you would see this here, and then the output would be set to 0 because of that. If it was 1, 0, and the current state was 0, then it would set the state to a 1, so that would become a 1. And you could essentially just be given a whole bunch of different combinations for SR and the current state, and then just have to give what the next state is. Or you might have to sort of work through a table of a single SR latch over time, or you might just be asked to like draw a circuit. Maybe not so much because we're online. You may not be asked to do that, but definitely be prepared to, in some capacity, at least describe this or something. Any other questions on SR latches? All right. So as a segue, SR latches are kind of weird, to be honest. You wouldn't really, you know, if I told you to make, at least conceptually design the interface for memory, it doesn't really make sense, you know, to say, okay, well, I'm gonna design my thing so that there's a control panel, you know, that has 2 buttons, S and R, and If you're not pressing any of the buttons, the state is just going to stay the same. So, maybe the state's up here and your button panel's down here. If you want to set it to 0, you have to press this button, and then it'll change it to a 0. Or if you have this button here and you set it to a 1, if you want to set it to a 1, you have to press this button, and it'll change it to a 1. And now, let's say you have a screen over here. Right, so on your right-hand side or whatever, you have a screen, and it's going to show you a number, and what you have to do is make that number appear on this screen. Well, what you're going to have to do is look at that number, say, oh, it's a 1, so because it's a 1, I have to press the S button to change this to a 1. Or if this is a 0, I have to press the R button to change this to a 0. Or if they're the same, I can just do nothing because it'll be correct either way, right? That's weird. Why shouldn't I be able to just take the wire that's connected up to this and then just hook it straight up to here? Right? And that's sort of the intuition behind how a D-latch works. So the way that a D-latch works is you have a D input, what's known as a clock input, or sometimes E for enable. In this class, we usually just use the word clock, though, for it. And then we'll have Q next again. And what's really nice about a D-latch is it just has an input that's data. You just take this D input here is for data. You just pass in what you want the D-latch to store, and if you set the clock to 1, it just stores that data, rather than sort of mucking around with having to set certain inputs to 1 in order to set to a 1 or to set to a 0. You just pass it the data you want it to store, and it stores that. And in terms of actual, what you might think of as memory, right? You don't want to have to sort of go to every single bit inside of the memory and specifically, light up a single input to set it to a 1 or a 0 based off of, whether you want to write the number 5 or 3 in somewhere in memory. So you'll see how this typically is much easier to work with, though it is more complex to make electronically digitally, because this is an SR latch. It's actually really, really basic. It's just 2 NOR gates or NAND gates, but and it's not really possible to make a more basic memory circuit unless you just do those 2 looping NOT gates. But that's not really, you can't interact with that in any way. You can read its output, but you can't change the signal. In order to do that, you have to do this. So for a D-latch, whenever the clock is 0, we'll just say that the output is just the current state. So for both of these columns here, it's just Q current because the clock is 0. And when the clock is 1, Q next is just going to be whatever D is. So you can draw the table like this, but I think it's even easier to write it out like this. So when the clock is 0, the next state is the current state. When the clock is 1, the next state is just whatever D is. And it's a lot easier to use D-latches for this reason. You can just pass in what you want it to store, and then just tell it to store it by changing the clock from 0 to 1. And then when you're done writing, you just change the clock back from 1 to 0 to just hold the state. And then you can just do whatever else you want in your computer or whatever. And then if you want to write something again, you just set that clock back to 1, write the data, and then change the clock back to 0. So now the problem is, how do you make this? Well, if you were just trying to just spit this out into a circuit, it might be a little bit difficult. However, we already have one memory component, right? We already have an SR latch that we could potentially use, and that we know that is able to store 0s and 1s. So it'll actually be easier to just use an SR latch in creating a D latch. So I'll start here with my D input and my clock input. And then I'm just going to draw a box here that's going to be my SR latch. Right? I'm just going to assume there's some sort of SR latch in here that works. It doesn't matter whether it's made out of NOR gates, NAND gates, it just works exactly according to that table. So the first thing that you want to do here is, well, let's look at this table. So this table is usually easier to understand how they work. This table is going to help us to make it. So let's see here. What's the best way to do this? Okay, so when the clock is 0, we want to pass in 0, 0 into this SR-latch, right? Because when the clock is 0, it's supposed to just hold its state. And the only way for this SR-latch to hold its state is for both of the inputs to be 0. How can we do that? Well, if we take two AND gates here, and we just basically put them in front of the SR-latch, and then let me move these back a little bit. So I'm essentially just going to inject sort of an AND gate into this, and I'll call these S and R again. But now I have this sort of second input that I'm going to pass into both, and we'll say that this is the clock. How is this useful? Well, no matter what I set S and R to, let's say I set these even both to 1, and I leave the clock to 0, well, 0 and anything is just going to be 0. So whenever the clock is 0 here, both inputs to the SR-latch are going to be 0, which means it's going to maintain, which is exactly what we want, right? According to this table here, we want whenever the clock is 0, which corresponds to these two rows, that QNext is just Q current. And if you look at the table up here for an SR-latch, the only way for QNext to be Q current is for both inputs to be 0. And so if we do this here, we've implemented the whole part of the clock. Well, now we need to do something for when the clock is 1. Okay, well, we have this D input here. When D is 1, we want this to turn into a 1, right? That's sort of the idea, is we want to store whatever D is in this SR-latch. Well, if you look at the table up here, the only surefire way to set the input or set the state of the latch to a 1 is to pass in 1 for S and R for 0, or 0 for R. So here we can just ignore the fact that we have this clock here. Well, if I take this 1 here and pass it in here, and then I just invert when I pass it into R, well, if this is a 1, this will pass 1, 0 into the whole thing, right? And we're assuming the clock is 1, so this will be 1 here. 1 and 0 is just 0, so that'll be a 0 here. 1 and 1 is 1, so that'll be a 1 here. And that will set the state of the latch to 1, which is exactly what we want. Well, if the data is 0 instead, well, if the data is 0, this will be a 0 here, this will be a 1. 0 and 1 is 0, 1 and 1 is 1. Well, if you pass in 0, 1 into an SR-latch, if you pass a 1 for R and 0 for S, it'll reset it back to 0. And so it'll store exactly what D is. And we're done, actually. So this right here is a D-latch. At least one way that you can make a D-latch with an SR-latch. Something I will note is that if you just sort of cut off the circuit where I had it before I added in this D input, that's just known as a clocked SR-latch. Or a gated SR-latch. It essentially is just a normal SR-latch, but you also add an extra clock input that allows you to just maintain state regardless of what S and R are. But the main ones to know are the SR-latch, which essentially just allows you to set the state to 1 or set the state to 0, and then the D-latch, which allows you to pass in what you want to store. And if you have a D-latch, what you could do at your work, is replace your whole panel with S and R with just, you just take that input panel that was on the side, you just remove it, and you just take the wire and you just connect the wires right up, right? It makes way more sense to do it that way, conceptually, in terms of actually writing information. Any questions on D-latches? Definitely don't be afraid to ask questions. I'm covering it how I think will be helpful to you, but if there's anything that you're not understanding, make sure to vocalize it so I can at least attempt to help you with that. Well, yeah. So this input is just called clock. It's not like normally this would be hooked up to an actual like sort of clock component, but really it's just an input, and it's sometimes also called enable, for like enable the write. So yeah, you can manually change this input to whatever you want. Typically in a computer, the only point to have it is to synchronize things that happen with the global computer clock. Whenever you hear, the computer's running at 3 gigahertz or whatever, that's the clock. The clock is doing 3 billion cycles per second, and it would be passed into and sort of wired across the whole computer to basically help to make sure that things are happening at a very specific time. And that's exactly what the clock is. That's why it's called a clock here, is because the whole point is to leave it 0 whenever you don't want to do anything. And then only when you actually want to do something, you change it to a 1 so that the writes actually propagate through. That's really why it's called a clock, is because it's similar to how a clock is actually used in a computer. But yeah, it's just a normal input called clock. So circuit-wise, no. Circuit-wise, you only really need to know how to do this. So this is a D-latch here, not a D flip-flop. Reason is because if, let's say, I set the clock to a 1 here, and I set D to 0, well, it'll store a 0 here. But if I leave the clock as 1 and I change D to 1, it'll then also change the state to 1. Which is a little bizarre, right? You might want to say it, okay, I'll give you some data, and then the moment that I turn the clock to 1, not whenever the clock is 1, but exactly when I change the clock from a 0 to a 1, I want you to take whatever D is and write it in. And if I change D after that, just ignore it. That is a rising edge D flip-flop. And that essentially, it just means is that instead of writing whenever the clock is 1, you only write whenever the clock changes. If you're only writing when the clock changes from 0 to 1, that's rising edge. And if you only write when the clock goes from 1 to 0, that's falling edge. Right? Because if you look at a sort of diagram of a clock, and you say this is 0 and 1, and you say, okay, well, it starts at 0 and then it rises to 1. You want to write it at this exact moment. And then if it's falling, you do it here. So rising is this one, falling is this one. And then like just a normal D-latch would write anytime here. Anytime in this window, it would work. I will not go through making the truth table for a full adder. You do not need to make the truth table for anything larger than a 1-bit full adder, because once you have a 1-bit full adder, you just chain them together to make however many bit adders you need. Full adders were covered in the lecture, so you can find all the materials from there if you need help with that. But it's just like any other combinational circuit. You want to just first come up, and for the lab here, you have complete liberty with how you want to implement. Or before I get into that, any other questions about the memory stuff so that I can wrap this up? But I'll get to your question.